Thanks everyone for coming. You're at the FireSim intensive, so we're going to talk about FireSim, which is our tool for doing scalable FPGA accelerated cycle accurate hardware simulation using cloud FPGAs. So I'm going to go through sort of what FireSim is in a second, but to just give you some background about what we're going to cover today, this is going to be extremely practical. So we kind of want to treat this as a tutorial. If you're interested more in the research background, you can see some of our previous talks and papers. We're also going to cram in a ton of info, but feel free to interrupt us with questions. A lot of the stuff that we're going to talk about is already in our online documentation. And we'll put up these slide decks and everything anyway. So to give you a sense of what we're going to talk about, we're going to start with talking about what FireSim is capable of, what we've demonstrated using FireSim already. Then I will talk about how you actually build and deploy FireSim simulations. Then David will talk about using FireSim to simulate custom hardware that you may have written in Chisel. Alon will talk about how you test and debug designs that you're simulating in FireSim. And then David will wrap up talking about community, how you can contribute, and sort of a broader conclusion. OK, so to jump up at a high level, what is FireSim capable of doing? Well, we can model hardware at scale cycle accurately. So we initially designed this to model data center scale systems. And so as a result, that's the example that I'll use throughout this part of the talk. But we'll talk about other sorts of designs later on. So in that context, we want to be able to model processors down to microarchitecture. And in particular, the way we're going to do this is automatically transforming them from Chisel RTL with Midas. Then we're going to integrate that with fast network and switch models. So these are software models that speak the same token language as Midas and can integrate into that environment. And we can also integrate novel accelerators just by way of automatically transforming Chisel RTL. As a result of having this fast FPGA-based simulation, we can run a real OS on top of all these simulated nodes, right? So we're going to boot Linux on these things and run real applications on top. And we'll show you how to build up complex applications easily on top of the system. And lastly, we want this to be productive and usable. So FPGA-based simulation has been done for a long time, but there's really been this lack of a common platform that people could use. And now that we have cloud FPGAs, we're aiming to make this broadly approachable to lots of different types of people. And we want to use this to encourage collaboration between both systems developers and architects, really bridging the boundary between those two fields. OK, so if we take a step back, David sort of covered this yesterday, but why do we want an FPGA-based simulator as opposed to just plopping RTL down on an FPGA? For the sake of example, we can say that we have some SoC that we want to tape out, right? And if we taped out this design, let's say it runs at a gigahertz, and we connect it up to DRAM, right? From the perspective of stuff running on the system, the SoC is going to see 100 cycles of memory latency. On the other hand, if we just put this on an FPGA, let's say it runs at 100 megahertz, but we're still attached to the same DRAM, right? If we didn't do anything special, if we just did FPGA emulation or prototyping, your SoC is going to see the wrong DRAM latency, right? And this is a problem if you want to measure software performance running on top of the system. So the way we fix this is that we take our RTL design that you see here, and we transform it. We apply Fame1 transform infertile using Midas. And then what we can do is we can tack on models that sit outside of this. I guess this pointer doesn't really work. So we can have models that sit on the FPGA fabric outside of this, like a DRAM model, that then is responsible for presenting the correct performance for whatever subsystem you're modeling to the simulated design. Yeah?
So just real quick, the reason why you don't do FPGA emulation is just because you can't run an FPGA at 1 gigahertz or
right.
whatever, so it doesn't make sense.
It's just fundamentally going to be clocked slower, so your IOs are not going to look performance correct. Yeah, so we can have these sorts of models sit on the FPGA fabric and then bridge to the outside world to provide accurate timing for things like IOs. So if we take a look at how people model systems today, right, there are a couple of options. First off, we can just say that we're going to build the real system, right, do a real tape out. This is really good for modeling reality, right? We have a single source of truth, we get the real thing, and it's very scalable. We just take more chips and hook them together. If we go to actual simulators, hardware-accelerated simulators really excel at having good simulation rate, right? And as a function of this, they can run real workloads or more of real workloads on top. But software-based simulators have a lot of pros too, right? They're generally easy to use. They're quick to rebuild because you're just recompiling code. And a result of this, they also run on commodity host platforms and are cheap. And if we look at prior work on building hardware-accelerated simulators, sort of the state of the art in academia, was previously a project called DIABLO. So DIABLO was capable of simulating thousands of servers, hundreds of switches, also modeling a data center type system. It's fast enough that you can boot Linux, run applications on top. The downside here is that you're handwriting abstract RTL models. So the RTL that's sitting on these FPGAs is not something you can go and tape out and get a real system that you would want to ship to people. And in some sense, this is actually harder than just writing tape out ready RTL. You have to have this notion in your mind that you are writing a simulator of some real piece of hardware. And as a result, you have to validate this against a real system. And on top of this, at the time, there were no cloud FPGAs, so this was tied to a custom host platform. Right? You had to buy this $100,000 rack of FPGAs you see on the right, pay someone to maintain it, and then if you want to share this infrastructure, you either have to have people build and buy and build the same infrastructure, or you have to support a big, wide range of different sorts of systems, which is a big pain. So to improve on this, we can take advantage of a variety of useful trends throughout the architect stack. The first of these is going to be FPGAs in the cloud, and I'll talk about that more in a second. Then the reason we're all here, we can take advantage of features in these high productivity hardware design languages like Chisel to automate the process of building simulators. Then we need something to simulate, and there's been a huge proliferation of these open silicon proven SoC implementations, and these implementations, many of them implement RISC-V, which is an ISA that now has broad software support. So once we build up our simulator on our individual simulated nodes, we'll be able to do things like boot full Fedora Linux and run Python applications on top. And of course, we also support sort of more classical benchmarks like running SPEC or Mcached or something like that. Okay, so at a 10,000 foot level, the way we're going to map FireSim onto our host platform is sort of shown on the right here. So the host platform we're going to use for this example that I'm walking through is an F1 16x large instance on EC2. So what this consists of basically is a beefy processor that you see on the left attached to 8 Xilinx UltraScale Plus FPGAs over PCIe. And so what we're going to do for this example is we're going to take our server simulations, right? This could also just be your arbitrary custom hardware written in Chisel. These are good fit to put on the FPGA, and we have the tools to transform them into a simulator that runs on the FPGA. So that's what we're going to put on the FPGAs. For our data center case, we're going to take our network simulations, and we're going to write those as software models that tie together all these individual FPGA-based simulations. So given all that background, let's actually build up a data center scale FireSim simulation sort of from first principles. So what we're going to start with is the RTL for a single server SoC. So our servers, in this case, that we're going to model are quad-core RISC-V rocket-based systems. We're going to clock the world as if these things are running at 3.2 gigahertz. That's parameterizable. You can change that to a different number. We're going to give it a relatively standard memory hierarchy, and we're going to tack on RTL for an Ethernet NIC. So in these examples, we're going to set the parameter of bandwidth so that this is modeling a 200 gig Ethernet NIC. But this is just the RTL. So now what we want to do is actually transform this into a simulator, and that's what we see here. So now this slice that we're looking at is a chunk of the FPGA. So this is the FPGA fabric. What you see in this light gray box now is the original RTL. We've transformed it using Midas, and we've tacked on these endpoints and models that you see along the periphery in the FPGA fabric. So the DRAM that you see on the left-hand side is the real physical DIMMs that are attached to the FPGA. And then we have a model sitting in between our real target design and the actual DRAM providing capacity so that we can model DRAM performance correctly. And then we also have these endpoints that model other sorts of IOs. So in particular, the NIC simulation endpoint is in charge of shuffling around tokens to maintain a globally cycle-accurate network simulation. So in terms of the specs that you see on the right-hand side, the only thing we've really added here is 16 gigs of DDR3. So the 16 gigs is provided, the capacity is provided by the real DRAM attached to the FPGA. The DDR3 part is being modeled by the DRAM model. And so if we put this down on the FPGA, we'll get a simulation rate of about 150 megahertz. And if we tack on the network, where now we have to shuffle tokens across PCIe every cycle, that's going to go down to 40 megahertz. So now what we want to do is scale out. So we're interested in modeling a data center in this case. So it turns out, conveniently, that we can fit 3 more copies of this simulator I showed you on the last slide onto one of these FPGAs. There are also 3 more memory channels that we can attach to. So in aggregate, on one of these FPGAs, we can model 16 rocket cores attached to 64 gigs of DDR3. And we can hook all of these up to a software switch model running on the Xeon attached to these FPGAs. And we can model a 4-node networked system running at 14.3 megahertz. So these things can boot Linux, communicate with one another, etc. So when you run this on Amazon, this simulation costs about 49 cents per hour to run. So there are instances that look like this, where there's just one FPGA attached to Xeon, and that's the price that you see here. But we're interested in modeling a data center, like I said, so we want to scale up. So now we're going to switch to running on an F1 16x large instance. So here we have 7 more FPGAs attached to the general purpose processor here. So we basically are going to stamp out 7 more copies of that 4 simulator chunk that I showed you earlier, and this is going to give us a 32 node simulation. There's still now a switch model. There's still a switch model running here on our regular processor that's maintaining global cycle accuracy for all of these 32 nodes. So every cycle, you can think of it as essentially exchanging a token between one of these simulators and a port on the switch model. And that's why we maintain global cycle accuracy. And so if you run one of these on EC2, this will cost $2.60 per hour on the spot market, or $13.20 per hour on demand. So the distinction between those two is that when you're running on the spot market, you're essentially bidding on unused capacity. And so if some other user places a very high bid, you can then get interrupted with 5 minutes notice and get killed. The $13.20 per hour number is, you request the instances, you're given them, and then they're yours until you turn them off. Nobody can stop you. So continuing on with this example, so what we're modeling here now is 32 of those quad-core RISC-V rocket-based server blades I showed you earlier with all these aggregate specs, and we're using 8 FPGAs running at 10.7 megahertz when you put this all together. So we want to continue scaling out. So now what we want to do is simulate 256 nodes. And the way we're going to do that is by taking 7 more of these F1 16x large instances, making them talk to another higher level switch model running on a regular EC2 instance. So now we've sort of added a level in our network topology, in our modeled network topology. And as a result, we can model this 256 node data center. And we can do the scaling out thing one more time and get to 1,024 nodes. So we can take that pod I showed you on the last slide, make 3 more copies of it at another level in the switching hierarchy, and network that all together. And so basically, we're using 256 FPGAs here to model 1,024 quad-core RISC-V rocket-based servers. And this whole simulation, globally cycle accurate, will run at 6.6 megahertz. So recall that we clocked this at 3.2 gigahertz, and so this is less than a 500x slowdown versus reality.
When you request these, quick question. So when you request these instances, is there some way to say you want it on the same rack? It needs to go through some switch, or what's the?
So you get sort of one level of tweaking, and that is you can create placement groups. So in these examples, we haven't done any of that optimization, just because it's generally very hard to get this many instances in one placement group. What happens behind the scenes when you request everything in a placement group is not public information. So I don't know that.
So FireSim, when it spins up these instances, does it use the spot pricing, instance?
So you can choose. So I'll show you like configuration files later on. There's basically like you can one-word change spot to on demand and request different types of instances. Yeah. Any other questions? Okay. Yeah. So sort of sum this up, we can take advantage of millions of dollars of FPGAs that someone else paid for. To simulate 1,000 nodes cycle accurately with this global synchronization. To us, when we run this even large-scale simulation, it only costs on the order of hundreds of dollars per hour. Obviously, much cheaper if you're interested in simulating smaller systems. Okay, so the point of this is that we've open sourced everything, and it's not useful only for just data center simulation. So what we've essentially built up in this process of needing to have all this automation to achieve this scale is basically an easy button for doing fast FPGA-based simulation. In all these examples, I talked about sort of modeling server types of systems. But you can replace these endpoints here with arbitrary chisel designs. And FireSim will automate the process of running all of these builds, running simulations, collecting results, building target software, all sorts of things. And you don't have to have a network. You can run tons of individual parallel simulations and so on. And we'll talk about all of these things as we go through the rest of the day. The high-level thing here is that all of this is abstracted behind the FireSim command line program. So if you've used like Docker or Vagrant or something like that, it's essentially the same idea, but for managing FPGA-based simulators. And so as a user, you only interact with this one instance, and everything behind the scenes is handled for you. And scripts can call this program to completely automate the process. So to give you an example, we had a paper at ISCA this year We have a bunch of plots in there running experiments. And we have basically one script that will regenerate all of those plots by spinning up simulations, running all the workloads on top. And this provides like true reproducibility. And you can write scripts to do other sorts of things. Like we have scripts to automatically run all of SPEC with full reference inputs in less than a day in parallel on 10 FPGAs. We've written tons of documentation, and we'll refer to that throughout today. And if you're an academic in particular, AWS provides large grants for using this stuff. So FireSim is completely open source and free, but you have to pay for the instances, the FPGA somehow. To give you a quick idea of the landscape, so we have a growing ecosystem, about 50 users signed up for our mailing list so far. I've talked to lots of people that are using this. We've started to integrate new designs into FireSim. So you can always bring your own, but we provide some defaults. So we provide Rocket Chip, obviously. We've integrated Boom now, too. There are a couple of projects that are publicly releasing FireSim images at the RISC-V Summit, including Pacha and the Keystone Secure Enclave. We've started using this from photonic datacenter modeling with Vladimir Stoyanovic's group at Berkeley. We've also started to integrate lots of new debugging features, and Alon will talk about all of these later on. And there have been a couple of user papers starting to trickle out at ISCA this past year, and as well as Micro. Okay, so to sum up what we can do, we can prototype scalable systems built on arbitrary RTL at an unprecedented scale. And you can always mix in software models when you want less accuracy or a faster model, depending on the trade-offs. These simulations are automatically built and deployed, as you'll see in more detail in a second. And we can automatically deploy workloads and stuff on top of these and collect results. And this is fully open source. You can run on EC2F1, and there's essentially no CapEx involved in running this thing. Okay, so some quick Administrivia before we move on. Everything we're going to show you today is documented at docs.fires.im. So these slides are sort of a high-level view of what's possible, and we'll sort of walk through everything, but you don't need to take notes or anything like that. And obviously the slides and videos will be online too. Okay, we already went through the agenda, so we just finished up the intro. So at this point, I'll take any questions about sort of high-level stuff before we dive in further.
I mean, I think I heard you say arbitrary chisel can just go on there,
yeah.
Right? But I thought in the Midas presentation yesterday, there's a bit of voodoo involved. So
yeah. So the real lacking feature right now is multi-clock. That's something that is being actively worked on by David and Albert.
And of course, if you have like a black box in your chisel, then we don't know what to do with that.
So. Okay, but if it is all, basically if you understood the entire clocking system, you are able to do the mapping.
Right. And yeah, if you have simple like Verilog black boxes or something that are simple designs, we have passes that will like clock gate from the outside to do this sort of transformation. Also.
Right. So there's someone working on a project locally at Cal where they're using HLS to generate like a rock accelerator, and so in that case, we've essentially black boxed the accelerator and we put like FPGA specific clock gating element in front of it, and that creates like the same sort of abstraction that we're
So you want to be able to stop the clock of something until the token arrives.
Right. So the easiest way to implement one of these FAME-style decoupled models is to have a single rule where you gate the clock until all of the input tokens are available, and you have space to enqueue all the output tokens in one atomic rule. Yeah.
Cool. Any other questions before we continue on? Okay, great. So I'm going to get started with sort of the practical stuff and talk about how we build and deploy simulations in FireSim. So what we're going to cover in this part is how we build FPGA images from some set of targets and how you specify them, choosing targets to actually simulate what you're going to deal with at runtime, how we configure target software, how we manage EC2 infrastructure, as well as actually going and running a simulation. And to wrap up, I'll talk about building a custom, complicated custom workload. And that in this example, it'll be building SPEC for a RISC-V-based system. Okay, so to give you some background terminology, this is terminology that we'll use throughout the rest of these talks. So there are three sets of sort of computers involved in a FireSim simulation. So there is you sitting here as the user. You're going to SSH into a manager instance. So this just looks like a regular server sitting in the EC2 cloud. And this is where you're going to run everything. So you, generally speaking, won't have to care about what's going on in these other two parts, but it's good to know that they're there. So then on the left-hand side, we have these chunk of machines called the build farm. These are essentially going to be dynamically launched and killed as you run Vivado builds inside FireSim. And that process is entirely managed automatically for you by the FireSim command line program. And then on the right-hand side, you can launch run farms, and these are essentially clusters that are in charge of running particular simulations. And you can have multiple run farms running at any given time. You can have multiple build farms running at any given time. They're all tagged. You can customize those tags, and we'll show you how to do that in a second. And the last piece of special terminology is sort of AWS terminology. So on AWS, a bit stream for the FPGA is called an AGFI, and so we'll refer to that throughout too. Okay. So if you're a first-time AWS and FireSim user, we also have a ton of extra background material that's in our documentation that basically shows you how to start with AWS from scratch. We're not going to go into details about that here today, but that's all on our website. So what we're going to assume now is basically you have a manager instance set up and you've cloned FireSim into your home directory. So our example that we're going to simulate here is going to basically be the system that you see on the left. So that's our target design. So we're going to have one node. It's going to be rocket chip based. We're going to configure it to have 4 cores, similar memory system as we saw before. But instead of having an L2 and RTL, we're going to model a 4 megabyte last level cache as part of the DRAM model. We're going to have same set of devices as before, just no NIC since we don't care about a network with one node. We're going to model a DDR3 memory system, and we're going to boot just plain old build root based Linux on top. The host resources that we're going to need for this are one manager instance and one F1 instance. So we already have the manager instance running. That's sort of what we did in the last step. And so now let's move on. So how do we use the FireSim manager command line program? So once you've cloned FireSim, you run the setup process. There's basically one source me script that you source, and you get all the FireSim tools on your path. So you basically get this FireSim command line program, and now you can run it wherever you want. So at a high level, the way you configure the manager is using these 4 .ini files. So there's build recipes, which sort of dictate what designs, what chisel configurations that you want to build. There's config build, which is going to list out the builds that you actually want to run at any particular time. And then I'll talk about the latter two in a second. So if we actually want to run a build, if we zoom into those first two, so if you look at one of these entries here, config build and build recipes basically just lists out a bunch of designs that you may want to have built at some point in the future. So if we look, for example, we want to model a quad-core system with no network. This is probably hard to read here, but we basically tagged this with the name FireSim quad-core, no NIC, DDR3, LLC4MB. And so if you look here, there's sort of 3 levels of configuration. David will talk in detail about what these are in his talk, but this is basically, these are basically parameters that are passed to the chisel build process when we actually build designs later on. I'm not going to go into detail about that yet. Next, you can also choose the type of instance that your build happens on. So we've sort of pre-selected C4 4x large instances. These are kind of vanilla EC2 instances. We found that using more expensive ones past this point is kind of past the point of diminishing returns. You'll get like 5 or 10% more performance. This deploy triplet thing is an advanced feature that we won't worry about yet. But basically what happens is throughout the build process, once you get an AGFI at the end, it's actually not just a bit stream. It also gets tagged with a bunch of extra information that FireSim will then use later on to actually deploy simulations to. So once we have this list of recipes, these are all things that we could build. But then we go over to this other config file, and this is how we're going to specify what we're actually going to build at any given time. So we can list out a bunch of configurations that we want built. In this case, we've listed all of these, but we can comment out ones that we don't want to run at any particular time. Then there's some setup stuff here. In particular, you asked about how we choose what type of market to get instances on. So for builds, there's a configuration option here where you can change a build instance market from on-demand to spot. And you can also set your bid price and stuff here and what happens to your instance when it gets terminated. So all those options are exposed here. You don't have to directly interact with AWS to do any of this stuff. OK, so let's say we've configured everything, and we have a build that we want to run now. So the way we actually run builds is through basically this command line, FireSim build AFI. And so what this is going to do in the background is launch enough instances to run all of your builds. It's going to run the FireSim generator, which kind of internally calls Chisel, Fertile, Midas, everything. It's going to then ship all of the infrastructure that you need to run a Vivado build onto one of these remote build instances. run the process, and then collect everything at the end. So collect QRR results, collect the final DCP, all of that information that Vivado generates. It pulls it back onto your one manager instance and puts it in the centralized directory of all your builds so that you can always go and inspect on what has happened, even though your build farm instances will get terminated once a build completes. And so that's basically the process of running builds. I didn't go into too much detail about how to do custom stuff yet, because David will talk about that in a second. But everything I showed you so far is just using vanilla configurations that are included with FireSim. OK, so at this point, I guess I forgot to mention, once a build completes, you basically get an email from the tool that tells you this configuration string that will copy into one of the other configuration files later on to specify the hardware images that we have access to. But we'll get back to that. OK, so if we look at our status now, we have basically our target design mostly ready to go, and we still have this one manager instance running. So
does it assume that it's the same symmetrical device in every FPGA, or can you switch?
Do you mean the thing we're modeling, or the FPGA itself?
What you're building.
Yeah.
So they're all the same.
So at this point, you can specify a set of configurations to build, and it'll build a variety of configurations, whatever you specify. They can be totally different. When we go to deploy, you can, so by default, there will be a configuration option in a top-level configuration file that kind of uniformly uses the same configuration for all of the FPGAs. But what you can do is there's actually like a custom user topology configuration also, where if you're doing a network configuration, you can instantiate a bunch of switches, some abstract notions of a FireSim simulation, and there you can build up like a heterogeneous thing by specifying those strings that I showed you earlier.
And the limitation is it has to fit in one FPGA.
Yeah, currently that's the limitation. Yeah. OK, so at this point we've built up our FPGA images, so now we want to build software to run on top of this system. And so what we want in this example is to boot Linux. So we basically want BBL, which is the Berkeley bootloader, with the Linux kernel image as a payload. And we want to build a root file system disk image so that it has something to boot from as all of our user space stuff. And so FireSim is going to give you two levels of workload automation. So there's FireSim software. This is a repo that's basically capable of building a variety of types of sort of base OS images. So the ones we currently support are a Linux-based image that's based on Buildroot, and then a Linux-based image that's based on Fedora. And so the way you do that, the way you build that basically is you cd into the FireSim software submodule in FireSim, and then you can run this Python manager that's capable of building these things in a variety of configurations. So in this example, it's going to spit out these two files. And if you want, you can change this to, for example, build an initramfs-based version, where all you get is this, this single image, no root file system. So for example, if you don't have a disk, but all the stuff that used to be in that root file system image is now baked into your BBL VM Linux image. And so there's a ton of documentation that goes into more detail about how to use that. But in effect, once we run these two lines, we have this whole system built up. And later on, that's going to let us run something called a Linux uniform workload. And we'll specify that string later on to say what we want to run on our system. There is another layer here that essentially lets us bake more complicated custom programs into these rootfs's. And we'll talk about this a bit later on. OK, so at this point, we've filled in the second to last check mark, which is we have target software to run on our system. So now we're going to wrap up our runtime configuration so that we can actually boot up. So if we zoom into these last two configuration files, we can now look on the left-hand side here. This file is called config hardware DB, and basically what you put in here are entries that describe images that you've already built. And so that email that I showed you earlier that contained that 4-line sequence, that's what you drop in here so that you can refer to these images by name. Basically, Amazon will give you this cryptic string that refers to the FPGA image. This sort of abstracts that away, so you get a nice name. You can also do things like override configuration triplets and stuff when you want to perhaps build a different software side of things than what's in the AGFI. By default, it's going to take the tags that are attached to this AGFI and get all of that information about the configuration process automatically. And then, once we have this database of configurations that we can run, so these are all things that we could specify as things we want to deploy, we're going to go over here and set up our actual run farm, essentially. So here, we describe our run farm. So the run farm, recall, is the collection of EC2 instances that we're going to deploy stuff onto. So we can tag it. By tagging it, we can basically have multiple collections of these things and have the manager manage multiple different simulations at the same time. Then within that run farm, we can configure different types of instances. So the ones we support so far are 16x larges, which are basically 8 FPGAs attached to the Xeon, 2x larges, which are 1 FPGA attached to the Xeon, and that's what we're going to use in this case, so it's set to 1. As well as M4 16x larges. We won't cover that here, but that's where we run switch models that are running without any FPGAs attached directly to them. Then, similarly to the build instance setup, you can configure the market that you're requesting these instances on, configure what happens if they get interrupted if they're spot instances, as well as choose a max price if you're on the spot market. So once we have that, that configures our host system. Then we need to set up our configuration for our targets, what we're going to simulate. So in this case, our topology is set to no network config because we're not simulating a network in this case. We just have one node and it has no NIC. And so we're going to set the number of nodes here to 1. If we had maybe many parallel benchmarks to run at the same time, like we will later with SPEC, we would set that higher and request more 2x larges. I won't go into detail with the rest of this configuration. These are all network parameters that we would use if we did have a network. The important thing, second to last important thing here is this default hardware config. So by default, when you specify this and you have a topology that doesn't individually override the configurations, what's going to happen is this default config is going to get applied across all of the simulations that you request. So in here, we're using FireSim quad-core, no NIC, DDR3, LLC4, and B. And so that's we're referring to this string here. It's a thing we just built in the build process. We pasted that configuration in here, and now we can refer to it as our default hardware config. And then lastly, we set our workload to Linux uniform.json. And I'll show you exactly what's in that JSON file a little later on. But that's referring to that build root-based Linux distro that we built earlier. Now, basically what we want to do at this point is actually launch our simulation infrastructure. So prior to now, we have not launched any F1 instances, and that's what we want to do. So you can run basically one command here, FireSim launch run farm, and it'll take whatever you described in that previous file and launch a run farm that looks like that. So in this example, you can see that it basically didn't boot any 16x larges or F1 or M4 16x larges, but it did boot up one 2x large, which is what we requested. And so at this point, we now have an F1 instance running. So if we look at our status so far, we basically have everything we need to run a simulation, including the FPGA instance itself. So the next step is to ship around all the infrastructure that we need to run a simulation. So recall that right now we're working on this one manager instance, just a regular EC2 node. And we have, for now, just one F1 instance remotely, perhaps many of them when we're running bigger simulations. And so what we're going to do to ship around all the infrastructure is run FireSim infra setup. And so that command is going to do a ton of things. It's going to do stuff like building the software driver. So this is the driver that speaks to whatever is on the FPGA. It configures all of the endpoints, controls how the simulation advances, and maybe talks to other software models. So it's going to build that. And in particular, the way it figured out how to build this whole thing, what commands to pass into the FireSim generator and then the Midas generator, is by requesting that metadata information from AWS that we tagged earlier. But you can also override this using that triplet stuff I showed you earlier. So now what it's going to do, it built the software drivers. It's going to ship around some extra infrastructure. It's going to clear the FPGA slot, and you'll see it flash the FPGA, as well as copy all of that driver stuff around onto the remote nodes. So at this point, it's going to set up everything you need to launch a simulation, including copying target software, all of that stuff on top. So next, when we actually want to run a simulation, given all this infrastructure has been set up, we basically do FireSim run workload. What that's going to do is start all of our parallel simulations, and then jump into this monitoring interface. So this monitoring interface will essentially keep spinning every 10 seconds and update you on what's going on in your simulated cluster. So basically, what it's going to show you up here is the whole list of instances that you have running. So these are all the run farm instances. In this case, we have no simulated switches, so it's not going to tell you anything about those. And then lastly, it'll list out all the simulated nodes. So here we just have one simulated node, and the job assigned to it is Linux Uniform 0. So the Linux Uniform workload is just going to give that same basic build root-based distro to every node that you simulate. And we'll talk about more complicated stuff in a second. So this monitoring interface will keep running as long as any of the simulations are running. And if we want to actually attach to a simulation, so this is the same monitoring interface I showed you before. If we want to actually attach to a simulation, we can see which instance is running a particular job. From our manager, we can just SSH onto one of these instances, and then the consoles for all these simulated systems are launched inside screens. So you can attach to a screen at any given point, scroll around in the system, as well as type stuff in once it's booted up. And at the end, if we have some leftover time, we'll show you a live demo. So now what about tearing everything down? So a lot of times, we don't just want to tear down everything, but we also want to capture things like workload results. And FireSim's workload system will support this, and we'll tell you how to specify what to capture in a couple of slides. But in this example, we have our system configured, let's say, just to capture that console output I showed you earlier and copy it back for all of your simulated systems. So basically, the way this is going to work is, in this mode, whenever it sees any simulation power down, it will copy back whatever you told it to copy back into a local directory on your system. So what happens is basically it'll print out a directory that tells you where all your results are stored. So you never, if you're running an automated workload, you never have to actually SSH onto those other nodes or anything like that. All of your results just show up in a directory on your manager instance. OK, last thing, we want to stop spending money. So once we're done running the workload, we want to tear down the actual EC2 instances. And so basically, you can run FireSim terminate run farm. It'll force you to type yes to confirm that you want to tear down all these instances, and then it'll do so. And so that's sort of the end-to-end lifespan of running a FireSim simulation.
And to be clear, you can have the runtime config essentially terminate a node immediately after the workload finishes. So if you're running something like SPEC, it will smartly save you money.
Yeah. Cool. Any questions so far? Yeah.
SSH to that IP address.
Yeah.
And SSH to the simulated
So in this configuration, since there's no network, you're SSHing into the host, and then once you're on the host machine that has all those FPGAs attached, then you can attach with screen to the console, simulated console of the simulated system.
That's what the screen command.
Yeah, that's what the screen command did. If you build a networked config, we can also directly interface. So we can add a port on the switch that interacts with a bridge on Linux, and then you can directly SSH into the simulated systems too. But we won't cover that here. But it's in the documentation. Any other questions? Cool. So I'll talk a little bit about how custom workloads work now. So I didn't point this out earlier, but the workload we specified, Linux uniform.json, actually corresponds to a real JSON file inside FireSim. So these JSONs for all these workloads sit inside FireSim/deploy/workloads, and they look something like this in a very simple case. So since this is a uniform workload, it's just specifying a bunch of common things that will be shared across all of the simulated systems. So they all get the same image, obviously a different copy of it, but this image that's from the beginning looks exactly the same. And so if we look at what's going on here, we're specifying the benchmark name. That's just a name that you can use to handily reference it. We specify a boot binary, so that is that BBL plus VM Linux image that we built earlier. There's some symlinking going on that you can look at in the actual repo to actually point into FireSim software. But we have that, and then we also have that rootfs image that's also symlinking into the built version inside FireSim software. Then these last two lines are sort of interesting from this perspective. So here we have two lines. One is common outputs. So what common outputs is saying is, once we tear down a simulation, I want you to actually mount the root file system. So mount this file system that the simulation was running out of, and copy these results out of it and give them back to me on the manager. So here, this is just kind of a garbage file, but you could imagine that you have some results that a benchmark wrote into the disk image of the simulated system, and you want to copy those back. And then we also have common simulation outputs. So here we're specifying UART-log, which is the standard way to refer to the logged console output of one of these nodes. And then also memory stats.csv that is logging information generated by the memory model if you've turned that on. OK, so let's look at a more interesting example of a workload now. So SPEC is something people commonly want to run. And so this, what you see on the right-hand side, is the JSON file, or at least the top of the JSON file, for SPECint 17, the int rate set of benchmarks with reference inputs. So JSONs here are used for sort of two things. So they're used how we already saw them, which is to know how to deploy simulations or what to deploy on a simulation. But we can also use these same JSONs to automate the process of building these rootfs and boot binary combinations. So you'll see a lot of similar stuff here, but what you'll see in addition is these separate definitions of workloads. So what we have going on here is we have some scripts that I'll show you in the next slide for generating the cross-compiled versions of the SPEC benchmarks for RISC-V. But what you'll see here is a bunch of base information. So the SPEC benchmark rootfs's are still based on the Builderroot-based distro that I showed you earlier. But what's going to happen is on top of that, we're going to stick in some special files to each one of these rootfs's. So when you want to run Perlbench, we'll get the Perlbench directory containing the binary and other stuff. And then we can also specify a command. So this is a command that will run automatically when the system boots up in the simulator. So basically what happens now is we have one of these workloads defined here. We get a customized rootfs built for that specific workload. So there's a rootfs built just to run Perlbench. It'll boot up on the simulator, run Perlbench as soon as it boots up, and power off. Once it powers off, the manager knows to collect results back from it. And so in this case, we have a common outputs directory. So each of these workloads will put their output into /output in the rootfs. So we'll collect that when a workload turns off. And then they'll also all have a UART log that we want to capture too. And so each of these workloads, so there are 9 more of them for the 10 benchmarks inside SPEC 17 int rate, will basically get 10 rootfs's to run on 10 simulations. And what we can do also is automatically build from the same JSON. So we don't have a ton of time to go into detail about how this works here. But if you go into FireSim deploy workloads make file, you'll see make targets for a variety of workloads. So you'll see one for SPEC 17 int rate and int speed. And if you run make SPEC 17 int rate, and obviously you have a SPEC license and disk image, you'll get 10 rootfs and Linux image combos that then can be deployed onto simulations. So you run that one make thing, you get this thing automatically built for RISC-V systems. Then when you actually want to deploy this, so we had that workload equals Linux uniform.json earlier. We can now just change that in that file to spec 17 intrate.json. And we can say we want 10 2x larges to run 10 simulations, and then set no net num nodes to 10. And then we can do the same process. Launch, run, farm, infra setup, run workload. That'll run each of those 10 benchmarks. As soon as a workload or one of the simulations completes, it'll copy the results back and terminate that 2x large instance. And basically, because you're paying for machine seconds on EC2, there's no extra cost to doing all these things in parallel instead of serially. OK, so to wrap up, as I mentioned earlier, don't fret if you didn't catch all this stuff. All this stuff is in our online documentation. And just to sort of sum up what we did here, we learned how to build as well as deploy FireSim simulations, and we learned a little bit about how to customize different workloads. And so with that, I'll pass it off to David, who'll talk about customizing the hardware that you want to simulate.
So I have a question regarding
Yes.
the build farm. So is there any plan to use some of your local machines to do the building and then deploy it on the cloud?
So
instead of launching the build farm,
yeah.
build everything locally, take it there and deploy on the FPGAs.
So by locally, you mean on machines that you own or on the manager itself?
On the machines we own.
Yeah, so on machines that you own,
Let's say we have all the Vivado licenses and
yeah,
everything.
so we don't currently support that. That is something, we welcome a PR for doing that, but it's not something that we do right now.
All right, so we're running pretty late, given that we started late. So I'm going to quickly try and cover how you can modify the target design. And by target design, I mean that graph that I was talking about yesterday. This is going to be really fast, so feel free to email me or ask a question on the Google Groups after. Yeah, so all the code references I'm making apply to FireSim version 1.4.0, which we released yesterday, is on master. There's a relevant docs section called targets right here, where most of this stuff is covered. So there are a number of submodules in FireSim, as I'm sure you've probably discovered if you've played with this before. There's Midas, there's Fertile, these both live in Sim. And then there's FireChip, which is a fork of Project Template.
in there, you'll find Rocketship, and Rocketship provides a number of key dependencies for Midas and also provides Chisel. And throughout this presentation, I'm going to be referring to some common source locations. Anything prefixed with an M is in Midas, F is in FireSim, and then, of course, CPP files will be in source main CC, Scala files will be in source main Scala. It saves me a lot of space on the slides. So from yesterday, I had this target graph, right? And Sagar talked a lot about how to stitch these things together to produce a larger simulation. But now I'm going to focus more on like how do you swap out individual nodes, or how do you add nodes? Right. So in Midas, this is a synchronous data flow graph. In a RAM-style simulator, it doesn't have to be an SDF, but for us it is. You have software models, transform RTL models, which are going to be generated from Turtle, and then abstract RTL models, which someone like me wrote by hand to consume and produce tokens. And yeah, like I said, FireSim basically stitches this star into a much larger graph by adding a NIC and then also adding like a switch model in software. Okay, so one of the gotchas is that target graph is not explicitly encoded anywhere. It's sort of implicitly captured in a variety of different places. So, as I said, the graph is a star because there's only one transform RTL model, and that's the turtle that you're going to pass to Midas.compiler. In simulation mapping, remember that flow graph I had yesterday? One stage called simulation mapping generates the actual token queues. By default, those are going to be 2-entry queues for decoupled I/O and 1-cycle pipe channels everywhere else. It doesn't have to be that way, but it is that way right now just to make sure we achieve good simulation performance. Because the initial tokens that you see the simulator with is dependent on the amount of target latency there is in each of these channels. And finally, the software and RTL models are bound during host platform mapping, which is that last stage I had in the flow diagram yesterday. And so things like the DRAM timing model, for instance, are generated there and bound to these token channels. And the way that works is each type of endpoint matches on a particular chisel type. And when we introspect on the I/O of the target you gave us, if we find, say, an Axie4 slave, we bind a memory model to that. And you can configure how to match on particular types of I/O by changing a config in a platform config, which I'll go into in a moment. Okay, so how can you change the RTL-Transformed model? Well, the easiest way is to interact with it like you would interact with Rocketship, and that is use the configuration system and pass in a particular parameterization. And in the config, like hardware DB recipes that Sagar had on one of his earlier slides, there were 3 variables: design, target config, and platform config. And these are all make variables that refer to specific like Scala classes, which encode a config or encode a Rocketship cake in the case of the design. So target config specifies like your classical Rocketship parameterization, right? So like, the size of your L1 caches, how many memory channels you have, how many cores you have, etc. Sim configs are platform configs. These are Midas level configurations. So if you want to configure like the type of DRAM model you're going to emit, or whether you want to enable debug features like assertion synthesis, you do this in the platform config. And it's important to note that the platform config can also see the configuration you pass to Rocketship. So all the parameters in Rocket's parameterization space are visible in this parameterization space. Okay. So if you want to do something more aggressive, maybe you have your own generator. There are 2 common approaches to replacing that green node altogether. If you have something based off Rocketship, the easiest way is to fork FireChip and then replace the submodule in FireSim with a submodule that points at your fork. You can also submodule FireSim into your chip project. Right. So the second way is if you have something that doesn't really resemble Rocketship, say it's like your own custom CGRA generator or whatever, you're going to have to add those Scala sources or add a submodule, and then you have to define an app that basically will call Midas.compiler, right? And so that will take your CGRA and perform this transformation on it and bind models to it, right? And you can do that. You can reuse a lot of the build system by adding your own make frag that's target specific. And so you can look at sim source main, makefrag, FireSim makefrag to get an example of what this looks like, or Midas examples. So all the target specific stuff lives in this makefrag. And the makefrag in sim makefrag is more target agnostic. Right. So on RTL and software models. So Midas provides a number of abstract models, including the DRAM model I mentioned yesterday, but also this default I/O model, which allows you to peek and poke unbound I/O coming off the target. So something like a GPIO or reset, you can set by writing to like memory mapped register that ties off that value. This is kind of low performance, so if you want to have a simulator that runs fast, you kind of need to write like your own custom endpoint. And so all of these software models below, which are provided by FireSim, have their own endpoint which does something clever with the tokens coming off the target so that we can achieve good simulation throughput. And this includes a NIC, serial I/O, which is transport for FESVR, a block device model, and UART. And yeah, all of these things live in F-Scala endpoints and FCVP endpoints. And I look at UART, which is probably the most simple example. So the thing about the target graph and about these software and abstract RTL models is that they're effectively configured twice. Like the graph isn't fully defined until you've programmed the simulator at runtime. So the two times are compile and generation time. Obviously, when you pick the kind of DRAM model you're going to generate, that partially configures it in a sense. And so if you pick a different platform config or you hack on the chisel sources related to endpoints, you're picking a different configuration of this graph, right? And of course, that applies to the CVP sources as well. You can just hack on CVP and then recompile very quickly. And the key thing to note is obviously if you generate a different DRAM model, you have to go through FPGA resynthesis. So you're talking about a couple hours versus 30 seconds, which happens during infra setup. All right, so the second time is runtime configuration. So all these abstract models, abstract RTL models and software models can accept plus args that change their behavior, right? And so for software, that kind of does what you expect. For hardware, it's a little bit more complicated. But for something like the block device, if you say plus block dev write latency, that's actually going to make a memory mapped write to a programmable register sitting on the FPGA. And so you can change the block device's write latency this way. And this is how the DRAM model is reconfigured as well. And so this can be affected by changing that config underscore runtime INI that Sagar brought up. They can also specify custom runtime config, which I'll get into in a bit. So this is sort of like only a subsection of that INI file that Sagar showed. But essentially, these things are things that are configuring the target in some way. They're just exposed in the INI. So you can change the link latency, for instance, of a networked target. And obviously, you can pick a different default hardware config by changing a string to point at a different AGFI. Yeah, and that's this right here. And so Sagar glossed over this, but you can change how you're building the driver, the software part, by specifying a different config triplet here. And that's those three design variables I was telling you about. Or you can pass a different set of plus args by specifying a file here. And like, for instance, by default, if it's left to none, when you generate the simulator, when you pass it through Midas, a bunch of default plus args are going to be placed in runtime.conf in the generated source directory. But if you want to, say, simulate a different DRAM subsystem without having to recompile the simulator, you're going to need to generate a different one of these runtime confs, which I'll get into in a bit. We're doing well with time. OK, so adding a custom model. So suppose you wanted to model something in software, or maybe you have like your own PCRAM model or something like this, and you want to bind it to the graph. The first thing you have to do is expose new I/O on your target that you can match on. So it needs to be a different Scala type, essentially. Then you're going to extend Midas endpoint to match on that type and bind your widget to the I/O of the channel. So there are two methods here, which will be clear if you look at Midas core endpoint. And then you need to add your endpoint to this endpoint map, which tells Midas, OK, if you see this type, please generate my endpoint. And so you can look at UART or block device and sim configs for examples of this. Then there's the software side. So now you need something that will interact with the memory mapped parts of that endpoint, perhaps to move tokens or perhaps to reconfigure like timing parameters. And so this basically works by describing a very small class that uses SIMIFs read, write, push, pull, which are sort of inter-FPGA CPU communication primitives to configure or to interact with a model. So then you have to register that class in FireSim top.cc, and if you look at the top of this file, you'll see a bunch of different models that are being programmatically added based on what's been emitted in that header that contains the memory map of the simulator. And so you can look at UART again or block device and FireSim top for examples. Okay, so the DRAM timing model. So generating that different runtime conf with the different plus args. So the DRAM timing models are pretty complicated. Like the multi-rank GDR3 models have something like 40 different arguments that you need to configure, and there are many ways to do it wrong in such a way that the thing breaks, or ways to do it wrong in such a way that you're not actually going to be simulating a like JEDEC standard GDR3 interface. So I will jump into that. That covers most of this. But so the key thing here is, like I said, there's going to be a default runtime configuration with all the plus args that sits in generated source, F1, target tuple, and target tuple is that tuple of design, target config, platform config. But if you want to generate a different runtime.conf, you can type make conf with the same tuple. So this is a video. Hopefully it works. But basically, when you type make.conf, the first thing it does is it regenerates the same instance of the memory model. So the problem here is like if you're generating, say, a latency bandwidth pipe, and it has some fixed width register to define the latency of that pipe, if you accidentally specify a plus arg that has a value that can't be encoded in that register, it'll overflow and you'll get a latency you didn't expect. So what we want to do is regenerate it, the instance, and use the actual like Scala class to legalize parameters that we're going to pass it at runtime. And so we've done that here. We've specified a DDR3 model with a first ready, first come, first served memory access scheduler, and we have this LLC with these configurable number of sets, configurable associativity, block size, number of MSHRs, and replacement policy. Oh, geez. Yeah. So now I'm going to actually interact with the configuration system. So I'm asking for a particular memory system size and a number of ranks. And then, so the challenge here is that depending on how big this memory system is, I need to pick a device with the right density. And so here I've picked a certain density, and it has profound implications on certain DRAM timings. So now, once I pick a speed grade, it's going to look up in a database that we have locally in Midas that will get things like TFA and the refresh cycle latency. And then here we're picking an address assignment, which is dependent on the kind of page policy you're using. And so all of this stuff in like DRAM Sim 2 is kind of punted to the user, but here we have this system that will let you legalize what you're trying to generate against the actual hardware that you've generated. And that's the end of my section of this talk. So if there are any questions, sorry that was really fast, I'll take them now.
The LLC that's doing snooping on the regular tiling plus?
This is a DRAM side last level cache that's sort of uncoherence behind the AXE4 interface that's presented to the DRAM controller. So this is a way to kind of sneak in a last level cache model without having to be coherent with the rest of the system.
Hi. So I'm going to talk about debugging, testing, and profiling because as much as you like the vanilla HDF5s of Boom and Rocket we provide, I'm assuming most of you are here because you tend to change your RTL or build new things. And whenever you write a new line of code, you'll also have a new line of bugs. So how do we do this with FireSim? So I'm going to talk about a few debugging methods that you can use. The first one will obviously be starting with software simulation because we start with micro benchmarks. We try to identify our bugs in software where we have the most visibility. Then I'll talk about FPGA-based debugging methods, so either ILAs or other features that we provide. And then I'll talk about how we are going to extend FireSim's debugging capabilities. So let's start with debugging using software. So FireSim has basically 3 levels of software debugging. So we call them target level simulation, Midas level simulation, and FPGA level simulation. I will emphasize FPGA level simulation is not actually an FPGA. It's just the most precise level. But basically, we have kind of a flow diagram here that says if you're just modifying the internals of rocket chip or boom, you change the branch predictor and you think it's going to do better, then usually target level software simulation will be enough. That's exactly the software simulation you get in Project Template and Rocket Chip because it doesn't have any external interfaces that we changed or had an impact. On the other hand, if we added or changed new endpoints, for example, if we decided to add a Gen Z interface or OpenCAPI, which means we need a new endpoint that has interaction with the host, then we start interacting with Midas, and we want to start running Midas level simulation or FPGA level simulation. So what's the difference between these levels of simulation? So as I mentioned, they're all software simulations, so they all use VCS, Verilator, or XSIM. In the target level simulation, the target design is untransformed. It's the pure RTL you got from your original rocket chip, boom, or chisel code. On the other hand, in Midas level simulation and FPGA level simulation, you get RTL after it's been transformed by Midas, meaning all those queues were added, all the clock gating was added, everything that was included in the same one transform. In the target level simulation, you have no host FPGA interfaces. So given that in the simulator, we are assuming you have interaction with host DRAM because that supports some of your memory model, etc. You don't get that in target level simulation, but you do get that in Midas level simulation and FPGA level simulation, but in different levels. In Midas level simulation, we are basically emulating the host interfaces. So you have a host DDR interface, but in Midas level simulation, we basically wrote a software model that behaves like that host interface. On the other hand, on the FPGA level simulation, you get everything that's been provided by Vivado and the FPGA vendor. So you get everything that's included in the F1 shell, which means their DDR controllers, their DMA controllers, their clock crossings, their width adapters, everything, which in the Midas level simulation is basically abstracted away using a software model. So just to try and illustrate this, if we take the slide that Sagar presented earlier about how the DRAM model interacts with the physical host DDR and how that interacts with the RTL design, then in target level software simulation, we're looking just at the RTL design, whatever is before it was F1 transformed, just your vanilla rocket chip project template. In Midas level simulation, we're looking basically on almost everything that's been that's going to be transformed into a bit stream, and we have this abstract model that models the host level, the host side DDR or host side DMA or other elements that interact with the host. And on FPGA level simulation, we get everything that's going to be transformed into the FPGA fabric, plus the host interfaces that are modeled by the FPGA tools.
So when you say you're doing the FPGA level stuff for the F1 shell, are you actually using like a LUT level netlist or some other model?
So in the FPGA level simulation, we're using XSIM from Vivado usually. So you get, it takes the IP, the Vivado IP, and incorporates that in the simulation.
It's pre-synthesis.
Yeah.
But it's pre-synthesis.
It's pre-synthesis.
Okay.
I mean, we could do like post PNR if we wanted to, but
Okay, you.
So just to give you a sense of how these different resolutions of simulations affect your simulation performance. Now, I want to emphasize this is not a comparison between simulators. It was using some default configs, but the main point to show here is that FPGA level simulation is very slow compared to Midas or target level simulation, and you don't really get a performance hit by simulating a Midas level simulation compared to a target level simulation. So if you're trying to debug something and you have even the slightest suspicion that it might interact with some Midas level issue, then we would recommend using Midas level simulation because it's basically the same performance as target level software simulation. And use FPGA level simulation only if you really couldn't find the bug and you're suspecting it might be with the interaction with the FPGA provided IP, the F1 shell, or anything of that sort. And we provide access to Verilator comes with FireSim, that's the open source version. You can use VCS if you have licenses for that. And XSim is the Vivado built-in simulator, so you can use that for the FPGA level simulation. So the practicalities of how to do that. So target level simulation is basically the same instructions as you run in Project Template and Rocketship. So that's within the target design FireChip directory, because FireChip is basically our fork of Project Template. Midas level simulation and FPGA level simulation are FireSim type simulations, so they are run within the FireSim sim directory, and they have their various make targets. So you can choose Verilator or VCS, and in XSim you choose XSim for FPGA level simulation.
So when you generate a Rocketship-based target, it emits a make frag that describes a bunch of recipes to run classical suites of tests, and we link those into our build system, so you can run the same run ASM tests in Midas level simulation as you would in target level simulation.
Yeah, it's the same set of assembly tests and test benchmarks.
And you're debugging the hardware, I presume, not the software executing on the host.
Yeah, this is, from these you'll get waveforms. You'll get VCDs.
So low-level
yeah.
hardware debug.
Yeah. One disclaimer, currently the FPGA level simulation doesn't support the DMA PCIS interface. It's a future to do. But sometimes software level simulation is not enough, and it can be from a variety of reasons. It's either we interacted with the Midas wrapper and everything looks fine in software simulation, but we couldn't find a bug, and we're sure there's somewhere to blame here, or our bug is just very deep into simulation. We booted Linux, we started running an application that needs to run on top of Linux, and we found a bug, and getting to that in software level simulation will take us a week and a half or 2 weeks. So for that, we are starting to use FPGA-based debugging techniques. So the first one is integrated logic analyzers, or ILAs. ILAs are these nice IP blocks provided by FPGA vendors. And they're basically probes that are wired up to signals in our RTL. And they constantly sample into a buffer of 1024 samples in this case. They're recorded in DRAM. And they're interfaced with our FPGA vendor's tool. And upon some trigger, you can dump these samples, and you can view them in a waveform. And this is how it looks in Verilog. You get this ILA module. You wire up the probes into the signals you want to probe. And in the case of F1 instances, you also have this debug bridge, because they have the whole shell and virtualization interface. And in the F1 instances, you can view the waveforms remotely. But we write in Chisel, and we don't want to interact with the Verilog too much, and we don't want to start instantiating the ILA blocks through Vivado manually. So we kind of automated this process for FireSim users. So basically, with a single annotation that's called FPGA debug annotation, we can annotate a Chisel signal in our source code, and that will automatically generate the ILA IP during the synthesis process. It will wire up the signals all the way to the top level and then wire them up to the ILA. It will connect it will set up the whole debug bridge and everything, so you can view the waveforms in Vivado through your manager instance, so you don't need to log into your run farm. To run this, you will need to set up the GUI in your manager instance, which is very well documented in the Amazon F1 instructions. You just run a script, and it sets up like a remote an RDP GUI.